Hi everybody, welcome to the next set of slides. This is lecture 12 on quality measurement. Assume we have a video codec. How do we evaluate this codec or compare it with other codecs? So this is, for instance, what we just saw with the PSNR for H.264 compared to MPEG-2. Right? So PSNR was an objective measurement to compare to CODA. And I already mentioned that this might not be the best. It's easy to compute, but it doesn't take into account properties of the eye, for instance. So especially if we use irrelevance reduction, the properties of the eye, the best would be a subjective test, where we have several test viewers look at images under controlled conditions and have them evaluate the decoded images or videos. This is called subjective quality measurement. Especially for small impairments, it is helpful to give the test viewers a comparison to the original uncoded video, as can be seen in the following picture, where there is a switch between the original and the decoded video. So that can be seen here. This is also from this book from Richardson, Video Codec Design. Here we have a source video sequence which is to be encoded. Then we have this video encoder and the decoder, and on the display the person looking at it, the subject, can decide which one he wants to take a look at, and in this way can compare fine differences, something that might be not so obvious without a comparison. So using this system, the test viewers then evaluate the quality according to a scale as in the following picture. So usually the test persons have this kind of scale where they can rate the performance of the two. And usually what is done is that it's not said which is the original and which is the decoded, but it's kept secret and a random sequence. So they just have to rate two sequences. One of them is the original, and the other one is the decoded. And for small differences, this is important because this also shows if the test person can actually distinguish between original and decoded. If they knew the order, they could imagine that there is a difference without really seeing it, and this avoids imagining a difference. Here we really know what the person saw. And this also allows us to estimate how reliable a test person is in this test. Because often the same sequence is presented several times and in different orders, and if the test person doesn't rate it consistently, then it's not so reliable. And here we have the scale between bad and excellent. So those five intervals, basically, 5 ratings. And on this quality scale, the test person has to evaluate each video sequence. So this is what I just said. Observe we have items A and B. Often one of the two is the original and the other the item under test, meaning the decoded video. In this way, it can be tested if the viewer recognized the original. A similar methodology can be found for perceptual testing of audio material. To measure small differences, it is useful to have trained test viewers, viewers who know where to look. The subjective measurement yields the most reliable result because it involves the human eye as the target for our application, as long as the eye is the intended viewer. The drawback of it is that it is quite time-consuming and expensive to conduct. To solve this problem, also objective measurements are used, measurements which can be done by using a computer or machine. So this is useful, for instance, if you have many items to evaluate, or you want to do a quick test. If you're an engineer for developing a system, this can be used for doing a quick test. The most well-known and most widely used in the context of video coding is the so-called peak SNR or PSNR, which we just saw in the comparison between H.264 and MPEG-2. If you compute the mean squared error between the original and the decoded video or image as mean squared error, which is the average of all squared differences of the pixels of original and the decoded version, then the PSNR is computed as in this formula. So this is the definition. PSNR is 10 times log base 10, so this is the dB, expression in dB. And here you can see we have the mean squared error in the denominator, right? Which means if we have a small error, then this number becomes big. And then we normalize it by this constant 2 to the power of n minus 1 squared. And this n here is the number of bits per pixel value. So usually when you have a color picture, for instance, or just the luminance, you usually have 8 bits, right? So that means n, small n, lowercase n would be 8. So in that case, this constant would be 255, and this is usually the case. And this normalization is important because the mean squared error is in the same number space, right? And the MSE hence depends on the number of bits. The more bits you have, the larger this mean squared error becomes, even though subjectively it doesn't really make a big difference. And that's why this normalization to the number range here is important. Basically, or effectively, it scales all the numbers to the range of 0 to 1. Yeah. So hence 2 to the n minus 1 represents the peak value in the image, usually the 255, and hence the name peak SNR. Observe that we conduct this calculation per channel, i.e. for RGB or YCB CR. The PSNR has the advantage compared to the SNR that it is independent of the internal representation of the image, meaning the number of bits per pixel. The SNR would change with the number of pixels, as I just mentioned. When we have more pixels, the number becomes larger, and hence also the mean squared error, which doesn't really say much about the quality. So that's why we do the normalization. So the advantage, it's very easy to compute, right? This formula is really quick and easy. Disadvantage, we need the original, which is not always available to be able to compute the mean squared error. And B, it does not correlate well with the human vision. It is only useful, for instance, to compare different versions of an algorithm because its basic artifacts would not change. And this was the case for H.264 and MPEG-2. So they have the same principles. They're transform based, they are motion compensated based, only different tools are used. And because it's the same principles, also the artifacts that appear in the decoded version are quite similar, and that's why this quality does not change, and it makes sense to use the PSNR for comparison. So the absolute value here is not so reliable as the comparison. Yeah, so this latter reason, the B, is the bigger problem because quality comparison is its main objective. So here you can see why the absolute value of the PSNR or the mean squared error doesn't say too much. So relatively it says more when you have the same type of artifacts, but the absolute number doesn't say much. So here you have two pictures, A and B, and they have this, almost the same mean squared error. So here you have A, looks nice and sharp, and here you have B, which kind of looks blurry, right? So observe that image A appears with a higher quality than image B. And this is because the faces are sharper in A, right? but the PSNR is higher for image B, saying that image B should have a higher quality. And this is because in image A, the larger background is unsharp. So when you look back on the picture, here the faces are selectively blurred, and these are the most important part of the image where people look at, right? Whereas here, the background is more unsharp. When you compare it here, the background here is sharper, and here it's less sharp. But usually people don't look much to the background. Often it's actually intended to be unsharp, so that people look at the faces. And yeah, that's why image A looks much better, right? Because people like to focus on faces. But the PSNR doesn't know the difference between pixels and faces or in the background. So that's why the PSNR is not really a good quality measure, just for comparison purposes. Yeah, so the PSNR does not distinguish between areas which are important for the eye, the faces, and areas which are unimportant, the background. Yeah, for this reason, there are works to improve objective, machine-based measurements to include properties of the eye to make the resulting quality score more similar to subjective measurements. One example is the so-called structural similarity measurement, short SSIM or MSSIM from Bovic et al., which emphasizes structure, meaning edges in images. And edges is again something that the eye likes to focus on, right? Because edges, they outline the boundaries of objects, so they give the brain a lot of information about what object it might be. So the brain focuses on those edges. So edges are important for visual quality, and this is what this subjective measurement takes advantage of. So this is the performance is illustrated in the following images. So here you have the original A. This is the original picture, and then you have several distorted images. So B here, you can see A is original, 8 bits per pixel, cropped from 512 by 512 to 256 to 256 for visibility. Right, so this is a part of an image. And then B is contrast stretched. So when you look at it, actually it looks good, right? It's almost no difference. I mean, the quality is quite high. You can see, for instance, that the black here is a little darker than the black here, and this is because it has higher contrast. The contrast was increased. So quality-wise, it's fine. And also the MSSIM gives it a score of 0.91 out of 0 to 1. So 1 would be perfect, and this is close to perfect. So good enough. Then C is a mean shifted image. Mean shifted means it's basically brightness. So every pixel gets a certain value added, and this is like increasing brightness on your display, for instance. And this is the result. So here you can see the gray areas here in the board become less gray, somewhat more light colored. And this is because of this constant addition of a value to each pixel. So it still looks okay. And that's why we have an MSSIM of 0.99, so almost perfect. So good enough. Then D is JPEG compressed. So you can take a look. Here D. Now the artifacts become quite obvious. So here you can see strong blocking artifacts at the edges of those bars here and the edges of the board. And also you can see artificial gray steps. So these are typical, albeit strong, JPEG artifacts. And it's good that it's strong because then it makes it easier to see for this demo. So here, this looks pretty bad, right? So MSSIM gives it 0.69. So it clearly reduced the rating. um, compared to the first two, which is actually corresponding to what the eye is seeing, right? It indeed sees much more distortions. Then next E is the blurred image. Basically blurring removes the edges. Edges are important for the eye, and this is the E. So indeed, this is a bad quality image, right? So the eyes thinks it's bad, and also MSSIM thinks it's bad because it only gives it a 0.7. Then we have a salt and pepper impulsive noise contaminated image, and this means we just flip the most significant bit of some pixels, and that means some black pixels turn to white and some white pixels turn to black. And this is also annoying, as you can see here in this picture, right here, those salt and pepper. This is easily visible because of the large error for a few pixels. And also MSSIM gives it a low rating of 0.77. Right. Yeah, and the interesting part here is that all of those distortions have the same mean squared error of 210. So if you would apply the PSNR, it would give the identical value for all the distorted images. So if you apply the PSNR here, then picture B and C would get the same rating as D, E, and F. Right? Even though clearly B and C look much better to the human eye. So that shows that this MSSIM gives a much better correlation to what the human eye is seeing. Yeah, so it shows it's actually quite well with the MSSIM, and not so good for the PSNR. So here's some other literature which you can find on IEEE Explorer within the TU Ilmenau network. Here an article from the IEEE Transactions on Image Processing in 2000, image quality assessment based on a degradation model from this group of Albovic. And then in 2002, at the International Conference on Acoustic Speech and Signal Processing, short ICASP, an article, a paper with the title, "Why is Image Quality Assessment So Difficult?" also from Albovic's group. Yeah, the area of improved objective measurement is still an active research area. And as I mentioned, they are all available on IEEE Explorer within the network of the TU. So maybe I can add that here. They are. Yeah, future coders often deliver higher resolution at lower bit rates, meaning we have fewer bits per pixel. This means we need more sophisticated models of vision, at least implied, in those coders to obtain a good perceptual quality. This means we also need more sophisticated models of vision for our objective measurement systems. So that's why development continues here. Okay, and finally, standards for representing digital video. So here are a few standards. The first digital standards were derived from the analog TV standards. And this is again from this book, Richardson Video Codec Design. So you can see some ITU standards, and you can see we have two different types. The 30 Hertz frame rate. This is for countries where you have a 30 Hertz power network frequency, and this is for instance the Americas. And then this set is for countries where you have a 60 Hertz power network, and this is 50 Hertz power network. So it's always twice that frame rate as the power network, and this is identical because when we have interlaced, then we have the half frames appearing at the rate of the power network. And this needed to be synchronized for early TV, because early TVs had cathode ray tubes with strong magnets to control the electron beam for scanning the screen. And you also had big power transformers, which also created a magnetic field with the frequency of the power network. And if the two are in synchrony, then any artifacts that appear from interference between those magnetic fields would be static and not moving. And static artifacts are much less visible than moving artifacts. And that's why we have those two sets of standards. So here the fields are the half frames, right, where you have even and odd rows. So here we have 60 Hertz identical to the power frequency, and here 50 Hertz again identical to the power frequency of those 50 Hertz countries, which are basically the rest of the world. So here we have the lines per frame. So 525 for the 60 Hertz countries, and 625, a little bit more for the 50 Hertz countries. So here we have slightly higher spatial resolution, but slightly less temporal resolution. Then we have the luminance samples per line. This is actually quite different, quite similar here. Then the chrominance per line, which is reduced because of the reduced resolution of the eye for color. Bits per sample, 8. That's the typical. The total bit rate for raw, uncompressed, 216 megabits per second. Right, this again shows the need for compression. Then here the active lines per frame, 480. And here you have less because in old cathode ray tubes you needed time for the electron beam to go from the bottom to the top. It's not going instantaneously, but the magnets controlling the electron beam needs to reverse the polarity of the magnetic field, and it takes energy to reverse that field and hence also time. So here we have the visible lines, and here for the Y components we get samples per line 720, and here we have the corresponding for the color components. And this is also, for this reason, quite similar to VGA. VGA was made originally such that it can be displayed on TV sets. So remember, VGA has 480 columns times 640 rows, and originally it was made for early computers to use TV sets as a display. That's why you have this correspondence. And then you have the derived standards here. We have 4CIF, which is quite similar to TV resolution. Then we have CIF, which is a part of it. And this was made originally for transmitting faces for video conferencing, reduced resolution, because it needed to be transmitted in the early days via DSL. Then we have even fractures of it, fractions. So I guess it's not really used much anymore. The common interchange format, CIF, is a widely used format for digital video. 4CIF has a resolution of 4 times the number of pixels of CIF and has a resolution similar to standard division TV, as I just mentioned. Okay, that's it for this set of slides. Thank you for your attention and see you next time.